Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 29, 2025, which is about 6 days ago. And this paper shows how to replace batch optimal transport pairing with a semi-discrete approach that pairs each noise sample to data using a learned dual potential, cutting the heavy quadratic precompute while keeping or improving results. The paper is titled Flow Matching with Semi-Discrete Couplings, and the implications for model training are quite significant. Beyond speed, the authors report straighter trajectories, better image quality, and a simple one-time fit with convergence guarantees, plus a guidance correction rooted in a generalized Tweedy identity. Alright, the introduction set the goal and the bottleneck. Figure 1 contrasts 3 strategies to pair noise with data during flow matching. The left panel shows independent flow matching, which assigns pairs at random and often yields curved paths. The middle panel illustrates batch optimal transport, where a batch of size n is optimally permuted, which can be unstable unless n is very large and therefore costly. The right panel presents the semi-discrete approach. First, fit a dataset-sized potential once, then assign each new noise by maximum inner product search across Laguerre cells. So Figure 1 introduced the pairing strategies. Figure 2 now shows convergence for the semi-discrete training. The chart tracks the estimated chi-square divergence as stochastic gradient descent progresses on ImageNet 32, which measures how close the learned marginal gets to the data distribution. Solid eta grad and dashed stochastic gradient descent both drive the error down, and larger epsilon, the green curve, converges fastest. The red dotted marker indicates when the learning rate decay started, after which the lower epsilon runs drop further. So the previous figure showed convergence trends. Table 1 now compares compute and memory across pairing strategies. The cached batch optimal transport needs about 2 times n times e memory, and pre-processing that scales, like n times e times d times n divided by epsilon squared, and training adds ad times n over epsilon squared overhead per step. Semi-discrete flow matching uses memory n and a one-time fit of size n times d times k, while training adds only d times n on top of the base gradient cost. Because theta dominates, this extra lookup is negligible. So the previous table summarized compute and memory. Figure 3 shows how improving the learned potential lowers chi-squared error, which in turn reduces flow curvature and improves FID on ImageNet 32. Solid curves report semi-discrete flow matching, and dashed lines mark independent flow matching baselines. The left panel tracks curvature shrinking as the potential sharpens, while the right panel shows FID dropping most for cheap Euler solvers with 4 or 8 function evaluations, then gains saturating near chi-squared, around 0.05. So Figure 3 linked better potentials to lower curvature and FID. Table 2 now reports headline FID numbers at 64 by 64. The table compares independent flow matching and semi-discrete flow matching across Euler and Dopre solvers for ImageNet and PetFace, unconditional and class conditional. Semi-discrete flow matching consistently lowers FID, with the biggest gains at small function evaluation budgets because pairing is stronger. For example, PetFace unconditional drops from about 57 to about 21, with Euler 4, and class conditional falls from about 48 to about 19. So the previous table highlighted FID gains. Table 3 reports Celeb A super resolution accuracy. The table compares independent flow matching and semi-discrete flow matching at 4 times and 8 times upscaling under noise sigma 0.1 and 0.2 with epsilon 0 or 0.01. Higher is better for PSNR, a fidelity score, and SSIM, a structural similarity score. Semi-discrete flow matching matches or beats independent flow matching across all settings. For example, about 20.4 versus 20.0 PSNR at 4 times under higher noise. Okay, the previous table compared super resolution scores. Figure 4 plots FID against time per pair, showing where pairing overhead sits relative to the red dashed gradient cost. Circles, the semi-discrete method, cluster at low time and low FID, while triangles for batch optimal transport shift right and degrade as batches grow. The top panels report ImageNet 32 across Euler and Dopre solvers, and the bottom panels show ImageNet 64 with PCA pairing. Color encodes epsilon, where smaller values generally yield better FID. Alright, 2 takeaways stand out. Learning a dataset-sized dual potential once makes optimal transport guided pairing essentially free at training time. and the resulting straighter flows deliver better FID and robustness, especially at low function evaluation budgets with convergence guarantees. The broader implication is scalable, practical optimal transport guidance for modern flow models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.